Good morning, everybody. How's everybody doing this morning? Right. So let's get started here, and hopefully, you guys are all had a good night's sleep. I did not because my baby is waking up all the time. But anyway. Regardless of that, let's get started here. And if you guys want to say hi, just so I can see who's here. And we can see if you guys have any questions before we get started about anything at all. And then we can also start looking at the homework that was due today and then get on to the new stuff. The new stuff, as I was looking at it, is actually something that we've talked about before, I believe, in chemistry. So, maybe you remember that, maybe not. But anyway, it's the new stuff I think is going to be a little bit easier. And then we'll be done. We'll be done with this chapter. Again, we're going to do a review on Friday. So I'm going to give you guys the review on Wednesday, and then we'll talk about the review on Friday, and we have a little test on Monday. Okay, so we're going to try to do some sort of little test every single chapter. And it'll all be the same kind of format, all free response, and it'll all be probably 4 or 5 questions, just depending on how much stuff is in the chapter itself. Okay, so if there are no questions, let's just jump right into the homework. The homework was all about springs, that mass spring system, and an oscillating mass spring system where you're looking at that simple harmonic motion of a spring and the mass at the end of a spring. And we said that the formula for that is going to be T equals 2 pi square root of m over k. And this tells us that the stiffer the spring, the smaller the period and the faster that oscillation, and the larger the mass, the larger the period, and the slower the oscillation. Okay, so looking at that, and I believe that we have rearranged this equation already. We can look at how to rearrange it for different problems, but let's just jump right into number 2 and see. I believe it's on page 607. So we can open that up, and this is what we got. So for number 2, we have when a mass of 25 grams is attached to a certain spring, it makes 20 complete vibrations in 4 seconds. What is the spring constant of the spring? So this is nice. We have to do a little bit of interpretation before we can actually solve this one. So let's see. Make sure I'm actually in the page here. Number 2. So we have a mass is 25 grams, but typically we want this to be in kilograms, right? Because all of our equations in physics depend on the fact that these units are always in the SI units. So grams are not SI. We need to convert that to kilograms, so it's going to be 0.025 kilograms, right? And then it's going to make 20 complete vibrations. So what in the world is that saying? So we're talking about 20 cycles, right? And there's 4 seconds for that. And so we can calculate the period, right? Because you have, essentially the period is going to be the time for one cycle, but we have multiple cycles, so the time divided by the number of cycles or number of waves. Okay, and so we have, what is that, 4 seconds? And we have a total of 20 complete cycles. So that's going to get us, so 4 divided by 20, or you can do that in your calculator if you want. 4 divided by 20. And that's going to get us a period of 0.2. So that means that one cycle is going to be 0.2 seconds because you have 20 cycles is 4 seconds. And that makes sense. You should have a cycle that's less than a second. If you can get 20 cycles in 4 seconds, right, that's going to be 5 cycles in 1 second, or 0.2 seconds for 1 cycle. So now that we have those numbers, we can go ahead and plug this into the equation that we have, right? Our equation up here is this, but we need to rearrange it, right? So it says, what is the spring constant? So we need to rearrange this to solve for K. And let's go ahead and do that. So I believe we've already spent some time rearranging it last time, but I'm just going to go ahead and do it again one more time first this time. So in order to rearrange this, we need to divide both sides by 2 pi. So this is going to be t divided by 2 pi equals the square root of m over k. Square both sides. That's going to get us t squared over 4 pi squared equals m over k. And if we're solving for k, we need to somehow get this up in the numerator. And there's a number of ways we could do this. I said probably the easiest way is to cross multiply. So that's going to get us k t squared equals 4 pi squared m. And then finally divide both sides by t squared. So k is going to equal 4 pi squared m over t squared. Now, what we want to do is we want to just substitute in for these different values that we have. And so let's come back over here. So that's going to be k is going to be 4 pi squared times m times 0.025 kg all over your period of 0.2 seconds squared. So let's do that. 4 pi squared times 0.025 divided by 0.2 squared. That's going to give us 24.67. All right, and I'm just going to round that off to 24.7. And if you remember, the units, you can leave the units as kilograms per second squared, but that's not normal for a spring, so we're going to convert that to newtons per meter. I would accept either one. It's fine. Okay? So, number 2, this is what we get. It's using the same kind of rearranging that we did for the sample problem, but you need to recognize what's going on here and how to calculate that period. So, just remember, probably the trickiest thing in this whole problem is the calculation of the period. Just remember, and think about, well, what does a period mean? The period is the time of one particular wave. And if you have more than one wave, you're going to need to divide by those number of waves in order to get the time of one wave. Okay? And we might need to do that later in terms of calculating frequency, and that would be kind of the opposite. Frequency would be the number of waves divided by the time. Period is the time divided by the number of waves. Okay, so number 3, and if you guys have any questions, just feel free to stop me and ask questions. If not, I'm going to go on to number 3. Number 3, we have, in this problem, we have, let's see, a 125 Newton object, and so right away we know that that is the weight of the object, and so we're going to need to convert that into a mass, and knowing that the weight is the force due to gravity, which is mg. The weight, the 125 Newton object vibrates with a period, and there we go, we have a period of 3.56 when hanging from a spring. What is the spring constant of the spring? All right, we can do that. So let's go ahead and assign those numbers and plug it into the equation that we have. All right, so our weight in this case is 125 newtons. And let's just go ahead and write down the period is 3.56 seconds. And the weight is also equal to mg. So mg is 125 newtons, which means our mass is going to be 125 newtons divided by 9.81 meters per second squared, which is going to be 125 divided by 9.81, which is going to be 12.74. Okay, so 12.7 kilograms. Okay, so now that we have that, we've got a period, we've got a mass. We can go ahead and just plug this into the equation. What are we solving for in this case? It's saying what is the spring constant? So it's the same thing, same exact form of the equation that we did before, right? K is 4 pi squared m over t squared. So I'm going to go ahead and plug that in. K is going to be 4 pi squared times the mass of 12.7 kg over your period squared, so this 3.56 seconds squared. So let's do that. 4 pi squared times the previous answer divided by 3.56 squared gets me 39.69, so I think we can round that off to 39.7. And once again, units are going to be newtons per meter. Okay? So, any questions so far? All right. If there are no questions, we'll jump on to number 4. Number 4. Number 4 is a lot like the sample problem, right? Basically, this sample is asking us now, rather than solving for the spring constant, right? So we have 2 more people get into the car, described in sample problem C. So the total mass of all 4 occupants of the car becomes 255. So now what we're doing is we're changing the mass, and we want to know, we haven't changed the car, we haven't changed the springs, so now it's going to change the period of the vibration of the car, and so we want to do that. All right, so let's go ahead and do that, see what happens when we just add a few more people. Now we'd expect most of the mass of the car is actually from the car itself, so we would expect that the period's not going to change a whole lot, right? We expect the period's only going to change a little bit. So let's see what it actually is. Okay, we have, looking back to the sample problem, we had previously a mass of, let's get rid of this one. We had previously a mass of the car. This is number 4 here. The mass of the car was what? It was 1275 kg. And the mass of the people before were 153 kilograms. And now we have a mass of, okay, it says all 4 occupants. So let me just erase that. So all 4 occupants have a mass of 255 kg. So let's just get that total mass. And remember, we're going to divide by 4 because we have 4 tires with 4 different springs on them. So that's going to be 1275 plus 255, and I'm getting a total mass of 1530 kg for the car and the occupants. And let's divide that by 4. Divided by 4, that's going to get me 382.5 kgs per spring. Okay. The spring constant, if you recall from the sample problem, we got a K value of 19974 newtons per meter. And so now what are we solving for? It says we want to know what the period is, which is fairly straightforward. We can use the original equation without rearranging it at all. So we have T equals 2 pi square root of m over k. So that's going to be 2 pi square root of 382.5 kg all over 19974 newtons per meter. So 2 pi times square root of 382.5 divided by 19974, which is 0.869. What'd you guys get? Do you guys agree? Hello. All right, so it's going to be 0.86948. I think we'll just round it out or just leave it at 0.869. And what are the units for period? What should it be? Period is a unit of time. Is it going to be minutes, seconds, hours? Seconds. Yeah, of course. So seconds for our period there. All right. Almost done here. One more problem. We got a spring constant that has 30 newtons per meter is attached to different masses and the system is set in motion. Find the period and frequency of vibration for masses of the following. So we're changing the mass and we want to know the period and the frequency. And so let's just get the period first. It makes sense to get the period. Anytime we're calculating the period, what we're going to do is we're going to use this equation right here, right? And I'm going to go ahead and work through 5a, and then we can just compare answers for B and C because they're all going to be worked out the same exact way. Okay? So 5a, we have this equation, right? T equals your 2 pi. And what does it say? We have a mass of 2.3 kg, and we have a spring constant. The spring constant is going to stay the same for all these problems, but the mass is going to change. So the spring constant in all these is 30 newtons per meter, which is going to be what? 2 pi square root of 2.3 divided by 30. All right, 1.74. We're going to round that up to 1.74, or technically we really only have two significant figures, but I'm just going to leave it at 1.74. And once again, units are seconds. All right, now one-step conversion, when we want to get the frequency, very, very simple. You could just do 1 divided by your answer, or even easier than that, there's a one-button way to convert between your period and your frequency, and that's this, x to the minus 1. That's going to be 1 divided by the answer, or the inverse of the previous answer. Hit enter, and then right away, we've got the frequency. And that's going to be 0.57. You can leave it at 0.57 or write 0.575. Either way is fine. Now, what about the units for frequency? Do you guys remember the units for frequency? We could write inverse seconds, but I'm going to prefer that we write hertz. So hertz as the units for frequency. So that's going to be A, and so you guys can check your answers for B and C. The only tricky thing for B is that you have to convert the mass to kilograms, right? So the mass is 15 grams, which is 0.015 kg. Once you have that, the process is all exactly the same. So for B, let me just write down the answers that I got. I said the period is going to be 0.14 seconds, and I think I just rounded off to 2 sig figs for that. And the frequency is going to be 7.1 hertz. And then for C, you've got, let's bump this up. C, you've got a period of 1.6 seconds and a frequency of 0.62 hertz. Okay? So the smaller the period and the smaller the period, the faster the oscillation, and the larger the frequency, the faster the oscillation. So just keep that in mind. So we can, when we compare these things and say, okay, which of these three is the fastest oscillation? Well, we'd say, okay, the B is the fastest oscillation. And does that make sense? The mass is the smallest. Yes, the smaller mass should be a faster oscillation. So that makes sense, right? Remember, the larger the mass, the slower the oscillation, simply because that mass is going to be acting as an inertia, which is going to slow down the motion. All right. So that's the whole homework. Any questions before we jump into the new and last section of the chapter? Okay. So it looks like you guys don't have a lot of questions this morning. It's good. I guess that means you guys are getting it. So the last part of this chapter, which is 11D, is all about the waves in general. So we're going to look at waves. All right, and this is going to be more to do with any kind of wave, not just simple harmonic motion, but it's going to have to do with propagating waves as well, right? So simple harmonic motion is just back and forth, but propagating waves, we're going to be talking about things like light, right? Or things like sound, okay? Or other things like that. And when we have these kinds of problems, the wave itself is going to have a particular speed at which it propagates through a medium or not through a medium, okay? And so these propagating waves all have a particular speed, okay? The speed, just like anything else, is going to be how far it travels in a given amount of time. So we have an equation for the speed of a wave in general, for the speed of any kind of propagating wave. It's going to be the frequency times the wavelength. And I'm going to use this equation. Your book, let me just, and we did it a little bit differently in chemistry, but I'm going to do kind of a combination of both. Your book uses the equation V equals F lambda. And there's a reason that I don't like that, or actually there's two reasons. The first reason is this really isn't a true velocity because there is no direction to this equation. Frequency and wavelength both have no direction, so your speed here doesn't have any direction, so it should be speed and not velocity. And the second reason is, if you recall back a long time ago when we dealt with these kinds of equations in chemistry, and we said, okay, the speed of light is going to be nu lambda or lambda nu. This nu represents the frequency and this is the wavelength, and so that nu looks a whole lot like the velocity, and so that gets to be super confusing. You don't want to end up with an equation that looks like V equals italicized V, because that's just going to be craziness. All right, so therefore we're not going to use this equation in the book just because you can end up with this craziness here. And so instead I'm going to just write out speed. All right? It's not a very long word, so it's going to be relatively easy. You're welcome to use S if you want, but I'm just going to say speed equals frequency times wavelength in exactly this format. Okay? So once we have this equation, everything else is going to kind of fall in place, okay? But let's kind of break down this formula and try to make some sense of it. All right, so this speed is going to be kind of in a, for anything, just like anything, it's going to be the distance traveled, right, per unit time, okay? What is the frequency? The frequency is the waves, the number of waves per unit time, and this here is the distance, or the length, we'll just say distance of one wave. Okay, so this kind of makes sense, right? So the speed of a wave is going to be the number of waves in a certain amount of time times the distance of one wave, right? So if this is waves, the waves, number of waves, times the distance of one wave is going to get us the total distance that that thing's going to travel in a certain amount of time. And so that's how we're going to calculate the speed. The speed is simply going to be the frequency. the how often these waves are going, and the distance times the distance of one particular wave. Okay? All right. So let's just jump right in to the sample problem, and then we'll be done for today. Okay? Sample problem, let me see. So you guys need to do a little bit of reading. Where is the sample problem? Page 619. All right, page 619. And this is a sound example. Okay, so on page 619, we have a piano string. A piano string that's tuned to middle C. It vibrates with a frequency of 262 hertz, assuming the speed of sound in air is 343. And now the speed of sound is going to vary greatly depending on what the sound is going through. Typically, the sound is going to go faster through more dense material. So speed goes fast, or sound goes faster through, let's say, solids than it does go through, let's say, gases. And so when it's going through air, this is going to be this is going to be a number you're going to see a lot. Okay, 343 meters per second. Find the wavelength of the sound waves produced by the string. Okay, so we have this equation where we say, let's first identify things here in the problem. So middle C, we have a frequency of middle C that's going to be 262 hertz, and we have a speed, because we know it's going through air, it's going to be 343 meters per second. And so the question says find the wavelength, so we want to know lambda or wavelength, and we have the equation speed equals frequency times wavelength. And so for finding the wavelength, we just divide both sides by f. So the wavelength is speed divided by frequency. Interestingly enough, so if we look at this equation, let's suppose that we knew the wavelength and we were solving for the frequency, it would look exactly the same. So in that case, we would divide both sides by lambda, and it would look like this. Frequency equals speed divided by lambda. And so either way, whether we're solving for lambda or solving for frequency, is going to be speed divided by your known. So let's just plug it into this equation right here, because that's the one that we have. It's 343 meters per second divided by the frequency of 262 hertz. And hertz are inverse seconds. So that per seconds over per seconds are going to cancel, and your units are going to be left as simply meters. So that is 343 divided by 262 is 1.3 meters. Okay, so that is how we're going to solve these kinds of problems. And I want you guys for homework, you guys can be solving, and we should actually have 1.31, because 1.309 should round up to 1.31, and we do have 3 significant figures on this one. Okay, so for homework, I want you guys to go through problems 1, 3, and 4, and they're going to be similar to this in nature, although some of them are going to be involving sound, some are going to be involving light, but you have the same equation for all of them. All right, you might need to look back, kind of some reference things. All right, so question here. Hey, Mr. Ketz, on Google Classroom, the homework says due April 29th. April 29th, really? Oh no, I must have accidentally hit the wrong day. No, your homework is not due April 29th. So your 11D is due tomorrow. Probably I was not looking at the right month. And that's probably what happened. And that was kind of just like the last Wednesday in April or something like that. So sorry about that. Because tomorrow is April 1st. Hey, that can be like an April Fool's Day joke, right? Oops, that's a really terrible joke. But anyway, no, the homework is going to actually be due tomorrow. The homework's actually going to be due tomorrow. Okay, other questions? Other questions? I will make sure to go ahead and fix what's on Google Classroom, and I think we will be done for today. Have a great rest of your day, and hopefully everything's making sense in physics, and hopefully these tests are working out for you guys. I know it's tough because we're not together, but at the same time it's also all open notes, so you don't have to memorize any equations and all that, and you can look back at your sample problems. And so hopefully this next test goes really, really well. And yeah, all right, so see you guys tomorrow, same time, same kind of thing that we're going to be going over, and that's it.